Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to be covering Le Chatelier's principle, the Van Hoff equation, and the relationship between thermodynamics and equilibrium. Let's start with Le Chatelier's principle. This principle says that if a stress is applied to a system that's already at equilibrium, the system's going to shift in whatever way helps relieve that stress and reestablish equilibrium. The stresses that we're going to focus on are changes in concentration, pressure, and temperature. The table that you see on this page summarizes some of the key points regarding how changing concentration, temperature, or pressure affect equilibrium, and then what the system does to reestablish equilibrium. So for concentration, when you increase reactant concentration, this favors product formation. When you increase product concentration, this favors reactant formation. For temperature, increasing temperature favors endothermic reactions, and decreasing temperature favors exothermic reactions. Finally, for pressure, increasing pressure favors the side with fewer molecules, while decreasing pressure favors the side with more molecules. Now, the statement of each of these points is very surface level. So I want us to spend time really exploring specific changes and their results using example reactions. Let's begin with concentration. Remember, when the concentration of reactants or products is changed, the system's going to shift to counteract that change and restore equilibrium. The first category we're going to discuss is what happens when we add more of the reactants or we remove some of the products. Whenever reactants are added, the system's going to shift in the forward direction to produce more products. When products are removed, the system's going to shift in the forward direction as well to produce more products and reestablish equilibrium. So to help us visualize this, let's look at the reaction of 1 mole of nitrogen gas with 3 moles of hydrogen gas to form 2 moles of ammonia gas. If we increase the concentration of the reactants, the system's going to shift in the forward direction to produce more products. If we instead removed product like ammonia, the system will also shift in the forward direction to produce more products. The second category for concentration is what happens when we remove reactants or we add product. When reactants are removed, the system's going to shift in the reverse direction to produce more reactants and reestablish equilibrium. When products are added, the system will also shift in the reverse direction to produce more reactants. So going back to our example, if we were to remove the reactants, the system will shift backward to regenerate those reactants and reestablish equilibrium. If we were to add extra ammonia, if we were to add extra product, the system will also again shift backward, this time to consume the excess ammonia and form reactants, which will help reestablish equilibrium. So the direction of the shift is always the system's attempt to undo whatever concentration change was applied. Next, we're going to focus on temperature effects. Temperature changes are a little different because they actually affect the equilibrium constant itself. So here, heat can be thought of as a reactant in endothermic reactions, and it can be thought of as a product in exothermic reactions. The first category for temperature is to look at endothermic reactions, where delta H is positive for the forward reaction and heat is absorbed. In endothermic reactions, again, heat can be considered a reactant. So, if you increase the temperature, it's like you're adding more reactant in the form of heat. So, the equilibrium shifts forward and more products are formed. If you decrease the temperature, it's like you're removing heat. So you're removing reactant. So the system shifts backward to favor the production of more reactants and reestablish equilibrium. So for example, let's take the decomposition of calcium carbonate into calcium oxide and carbon dioxide. This is an endothermic process because it requires heat. If you increase the temperature, the reaction shifts towards producing more product. If you decrease the temperature, it shifts back towards producing more reactant. The second category for temperature is to look at exothermic reactions where delta H is negative for the forward reaction and heat is released. In exothermic reactions, heat can be considered a product. So if you increase the temperature, it's like you're adding more product. And if you were to add more product, the system shifts backwards towards the reactants to reestablish equilibrium. If you decrease the temperature, then it's like you're removing heat, hence you're removing product, and the equilibrium shifts forward to make more products and reestablish equilibrium. A good example is to go back and look at our ammonia reaction. This reaction is exothermic. So at higher temperatures, the equilibrium shifts backward towards nitrogen and hydrogen. But at lower temperatures, it shifts forward towards producing more ammonia. Finally, we can look at pressure effects. These changes only apply to equilibria that involve gases because solids and liquids do not compress. The system's going to shift to counteract the pressure change by changing the number of moles of gas. So when pressure increases, the system's going to shift towards the side with fewer moles of gas. And when pressure decreases, the system will shift towards the side with more moles of gas. Why is this the case? Let's really think about it. Pressure in a gas system is related to how many gas particles are bouncing around in a given volume. If there are more moles of gas, that means more particles colliding with the container walls, which increases the pressure. If there are fewer moles of gas, there are fewer collisions, which decreases the pressure. So when you increase the pressure on a system at equilibrium, the system is going to respond by trying to bring the pressure back down. And the only way it can do that is by shifting towards the side of the balanced equation that has fewer moles of gas, because fewer gas molecules mean lower pressure. On the flip side, when you decrease the pressure, the system wants to bring it back up. And it does this by shifting towards the side with more moles of gas, since more particles in the gas phase increase the pressure. So for example, going back to our ammonia reaction, nitrogen gas plus 3 hydrogen gas molecules are in equilibrium with 2 ammonia gas molecules. So on the reactant side, there's a total of 4 moles of gas, and on the product side, there's only 2 moles of gas. If you increase the pressure, the system is going to favor the side with fewer gas molecules, which in this case is ammonia on the product side. But if you decrease the pressure, the system will favor the side with more gas molecules, which means it shifts back towards nitrogen and hydrogen in the reactant side. Now, if you're curious about volume effects, it's really easy to think about because pressure and volume are inversely related. So, if you decrease the container volume while holding temperature constant, the gas particles have less space to move around, so pressure goes up. If you increase the container volume, the gas particles have more room, so pressure goes down. So when we describe Le Chatelier's principle in terms of pressure, you can just as easily describe it in terms of volume. If volume decreases, pressure increases, and the system responds by shifting towards the side with fewer moles of gas to reduce that pressure. If volume increases, then pressure decreases, and the system responds by shifting towards the side with more moles of gas to bring the pressure back up. Now that was a lot of information, so let's quickly summarize. the main takeaways from Le Chatelier's principle. Concentration changes. The system shifts to counteract the change, moving away from added species or towards removed species. For temperature changes, for endothermic reactions, increasing temperature favors products, while decreasing temperature favors reactants. For exothermic reactions, increasing temperature favors reactants, while decreasing temperature favors products. Then finally, for pressure and volume changes, the system shifts to produce fewer moles of gas when pressure increases or volume decreases, and it shifts to produce more moles of gas when pressure decreases or volume increases. Let's go ahead and apply this to a practice problem. The problem here asks, this endothermic reaction will shift to the right under which circumstances? And the reaction we're given is dinitrogen tetroxide forms 2 moles of nitrogen dioxide. And the problem tells us this is an endothermic reaction. That means heat can be thought of as a reactant. So if we increase the temperature, it's like we're adding more reactant and the equilibrium will shift to the right to produce more products. So increasing temperature favors the formation of nitrogen dioxide. Now let's consider pressure. On the left side, we have just 1 mole of gas. On the right side, we have 2 moles of gas. So if we increase the pressure, the system is going to want to relieve that stress by shifting to the side with fewer moles of gas. That would be the left side. So increasing pressure does not favor the right side, it favors the left side. Finally, let's think about what happens when we increase the concentration of dinitrogen tetroxide. Adding more of the reactant pushes the equilibrium forward, so it shifts it to the right so that more product is formed. Putting this all together, increasing temperature and increasing the concentration of the reactant are going to shift the reaction towards the right. But increasing pressure shifts the reaction towards the left. All right, let's connect now Le Chatelier's principle to the math that predicts how K changes with temperature. The idea you already know that we just discussed. It's qualitative. If a reaction is endothermic, heating pushes it towards products. If it's exothermic, heating pushes it towards reactants. Now, the Van Hoff equation, it's going to be the quantitative version of that idea. Here is the key relationship that we're going to use. The natural log of K2 divided by K1 equals the enthalpy of the reaction divided by the gas constant multiplied by the difference between 1 over T1 and 1 over T2. K1 and K2 are the equilibrium constants at 2 different temperatures, T1 and T2. And T1 and T2 are the 2 different temperatures. They have to be written in Kelvin. R is the gas constant. We usually use 8.314 joules per mole per Kelvin if the enthalpy is given in joules per mole. The sign of delta H, that's going to tell us everything about the direction of the change. So then how do we begin to understand this equation? To do that, we're going to have to think about the 2 pieces at play here on the right side of the equation, temperature and enthalpy. First, if T2 is larger than T1, then the term in the parentheses, 1 over T1 minus 1 over T2, that term is going to be positive. But if T2 is smaller than T1, then that term becomes negative. Then you're going to have to multiply that by the sign of delta H. If delta H is positive, that means the reaction is endothermic, and then raising the temperature makes the whole right side positive. If the right side of the equality is positive, then for the natural log of K2 over K1 to also be positive, K2 needs to be larger than K1. In other words, heating favors products for endothermic reactions. You can apply the same logic to see that cooling an endothermic reaction does the opposite. It makes K2 less than K1, and therefore the reaction favors the reactants. If delta H is negative, meaning the reaction is exothermic, then the opposite happens. Raising the temperature makes the right-hand side negative. If the right-hand side of the equality is negative, then for the natural log of K2 over K1 to also be negative, K2 needs to be smaller than K1. In other words, heating favors reactants for exothermic reactions. You can apply the same logic to see that cooling an exothermic reaction does the opposite. It makes K2 greater than K1, and therefore the reaction favors the products. That's the logic you want to carry with you. For endothermic reactions, temperature up means K up. For exothermic reactions, temperature up means K down. Another way to see this is to imagine plotting the natural log of K versus 1 over T. That relationship is linear, and the slope of the line is negative delta H divided by R. So the steeper the slope, the larger the enthalpy change of the reaction. And here's a really cool connection. The Clausius-Clapeyron equation that we use for vapor pressure, it is actually a special case of the Van Hoff equation. In that case, delta H is the enthalpy of vaporization, and K is directly related to the vapor pressure. This is why plotting the natural log of vapor pressure versus 1 over temperature gives us a line with slope equal to negative delta H vaporization over R. Let's go ahead and apply this to a practice problem. The problem says, consider a reaction where the enthalpy of reaction is negative 212 joules. Which pair of K values and temperature is possible for this reaction? So the first thing we want to do is we want to recognize that the enthalpy here is negative. So the reaction is exothermic. That means when the temperature increases, the equilibrium constant must decrease. Keeping that in mind, we're going to begin to look at the answer choices. A says none of these, okay. B says that K1 is 10.5, T1 is 100 Kelvin, and then K2 is 9.33, and T2 is 327 Kelvin. So in option B, the temperature goes from 100 Kelvin up to 327 Kelvin. That is an increase. And then the equilibrium constant, it decreases from 10.5 down to 9.33. That matches perfectly with exothermic behavior. So this answer is the correct answer, but we're still going to work through C and D. In option C, K1 is 21, T1 is 111 Kelvin, and then K2 is 21 and T2 is 316 Kelvin. So in option C, the temperature increases, but the equilibrium constant stays exactly the same. That would only be true if delta H were 0, which it isn't. Then we move into option D. K1 is 14.6, T1 is 122 Kelvin, then K2 is 16.6, and T2 is 315 Kelvin. So in option D, the temperature increases and the equilibrium constant increases as well. That would be correct for endothermic behavior, not for exothermic. So that means the correct answer here is option B. The reason A is not true because it says none of these, and we already found a consistent match in option B. All right, let's finish this lecture by connecting Gibbs free energy to the equilibrium constant. This relationship is one of the most important links between thermodynamics and equilibrium. So we're going to start with the general Gibbs free energy equation. Delta G equals delta G naught plus RT times the natural log of Q. Here, delta G is the free energy under any conditions. Delta G naught is the standard free energy change. R is the gas constant. T is the temperature in Kelvin. And Q is the reaction quotient. Now, at equilibrium, Q becomes equal to K, and delta G equals 0 because this system is balanced and no net change is occurring. If we plug those conditions into the equation, we get 0 equals delta G naught plus RT times the natural log of K. Rearranging gives us the key expression that delta G naught equals negative RT times the natural log of K. So, what does this actually mean? This tells us that the size of the equilibrium constant is directly tied to whether a reaction is thermodynamically favorable under standard conditions. If K is very large, the natural log of K is positive, and multiplying by negative RT gives us a very negative delta G naught. That means the forward reaction is spontaneous, and the equilibrium position lies far to the right, favoring products. On the other hand, if K is very small, much less than 1, then the natural log of K is negative, and multiplying by negative RT makes delta G naught positive. A positive delta G naught means that the forward reaction is non-spontaneous under standard conditions. So the equilibrium position lies to the left and it favors reactants. Finally, if K equals 1, the natural log of K is 0 and delta G naught is also 0. That means the system is actually perfectly balanced under standard conditions with neither reactants nor products strongly favored. The key takeaway here is the direct link between magnitudes. A large negative delta G corresponds to a very large K, meaning the system strongly favors products. A large positive delta G, that corresponds to a very small K, meaning the system strongly favors reactants. And a delta G equal to 0 corresponds to a K near 1, meaning both sides are present in comparable amounts. They are in equilibrium. So let's take that and apply it to a practice question. This one says, what is the value of delta G naught if K equals 10 to the 17th at room temperature? So here we're going to use delta G naught equals negative RT natural log K. And we're going to go ahead and start to plug numbers in. R is 8.314 joules per mole per Kelvin. T is room temperature, which is going to be approximately 298 Kelvin. That's room temperature. 25 degrees Celsius is room temperature. You add 273 to that, you get 298 Kelvin. And then K is 10 to the 17th. So plugging these values into our calculator, we're going to get the answer is about negative 97 kilojoules per mole. That negative value makes sense because K is extremely large here, and that means the reaction strongly favors products. So delta G naught must be strongly negative, and that's exactly what we got. And with that, we've completed this lecture. I hope it helps. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.